Off we go. Let's wrap up these slides first on game theory, and then we should have enough time to start some new ones, and then that'll be it. That'll be all the content in the class. So that's kind of exciting. So yeah, we learned about the prisoner's dilemma last time. It's like, weirdly enough, it's better to confess. Even though there is a way to get out without any time in jail, you can't control the other person. It was a non-cooperative game, and so sadly, you're forced to do it right, okay? To do it a little bit differently than you might think. Here's another game idea. Maybe you played this with a sibling before. It's called cake cutting. So actually, the internet is not in agreement as to whether this is a cooperative or non-cooperative game. I could see it being either, honestly. I could see it being non-cooperative because, like, when you cut the cake, the game was, right, one person cuts the cake, like you cut the cake, and then your sibling gets to pick which slice they want, right? And that's supposed to keep it fair. Cooperative means that alliances are good, and non-cooperative means that you're kind of forced into an alliance. Alliances equals good. That's what cooperative games are. A non-cooperative game, like you're forced into an alliance, and maybe this is that case as well. I could see either way. So I guess the cooperation is kind of forced upon you. So maybe it's a non-cooperative game, but this is the game of cake cutting, right? One person cuts the cake, and then it's the other person's job, there's two people, to decide which piece of the cake that they want after you've cut it. So the right way to play the game, of course, assuming you want a lot of cake, is to cut the cake exactly in half, right? Because the second you do that, let me draw it like this for three-dimensional effect. The second you do that, then it doesn't matter which side your sibling picks, right, or the other person picks, because they're of equal size. You're never gonna get the bad piece. Okay, so that's always the optimal strategy for cake cutting, because the second you cut the cake in a silly way, assuming your goal is a lot of cake, if you cut the cake like this, right, you know that your sibling is going to take this piece if they get to choose. So that's the idea. That's why, yeah, it's best to cut the cake in equal pieces. So that's like a game. And there's a property of this game that kind of describes like why we pick this one. And then also some other things. So it's called Pareto optimality, just like a Nash equilibrium was kind of the solution to the prisoner's dilemma problem. Cake cutting, you can think of Pareto optimality as the best way of cutting the cake. Okay, so it has to do with allocating resources, like giving food to people, giving cake to people, giving places to live out. So a resource allocation, we call it Pareto optimal, if you were to change the allocation, this is a weird definition, if you were to change that allocation, if you were to change the way you cut the cake, for example, and handed out the cake to people, it will always leave somebody worse off. Okay, so it's a very utilitarian kind of idea, I would say. So what are some Pareto optimal allocations for cake cutting? So you ask the question, like, which kinds of cuts of cake would leave somebody worse off if you changed them? Let's go back to our most optimal idea of cake cutting. This is Pareto optimal, right? Because look, if you cut the cake like this, if you were to change the way you cut that cake, like maybe you cut a little bit more over here, do you see how now, like you've split it up and somebody gets a smaller piece out of the deal now? Somebody will get a bigger piece, but somebody gets a smaller piece, and it's probably you because your sibling's going to pick. And so that is what it means to be Pareto optimal. So like cutting this cake in a different way would change the outcome. It would leave somebody worse off. So cutting the cake exactly in half is Pareto optimal. And actually, surprisingly, every way of cutting the cake is Pareto optimal. Watch. That's a little weird to think about. So there's more to it for sure, but this is kind of interesting. Like here's a cake cutting. Here's an allocation of the cake. Do you see how and your sibling will pick the giant piece, of course. If you change the way you cut the cake and you made it like this instead, like from here to here, do you see how like your sibling's still going to take the bigger piece, but it's less of a bigger piece now? So they're worse off. So it's also Pareto optimal to cut the cake in this way. Interestingly enough. So yeah, that's one way to think about like outcomes and whether or not they're good. One way to check for it is Pareto optimality. you kind of want both people to be happy with the cake cutting at least. But I can also describe the prisoner's dilemma. The Nash equilibrium that we found for the prisoner's dilemma happened to be a non-Pareto optimal outcome. You think about it, there was a way, right? There was a way to make both people happy for this one, right? And this would be, maybe this is the Pareto optimal one. Like, nobody's going to be worse off if you change it. But this, like, if they both confess that was the outcome that we said was going to happen, that's not Pareto optimal, right? There's a way to get to here, right? There's a way to get to here, and that's a better outcome for everybody. So it's not Pareto optimal. And that's kind of, that helps explain, that gives a reason why that prisoner's dilemma problem was so weird to us. Like, it seemed wrong. Like, that was the answer. It was not Pareto optimal. So we like to be fair in our thought process, in our brains, I guess. So that's a fun new idea. That's a new game. Does that make enough sense? Not too horrible. Next, I want to talk about how to share the bill with somebody, because that's a fun thing that's useful in life. Let's say you get in an Uber or a taxi. You get in an Uber and you share it with your friend, and your friend lives on the way to your house. All right, so here's the setup. Fair taxi rides. It's a cooperative game because you want to share a taxi. It saves you both money. So, for example, two people are sharing a taxi, Alice and Bob. So here's my best drawing of a taxi. I think it's facing the wrong way, but you get the idea. Like, there's the front of it at least. And you want to go home, and so does your friend. So Alice lives right here, and then Bob lives over here, and Alice lives on the way to Bob's house. There's no going out of the way, so that's nice. So of course they're going to share a taxi, just like have Alice step out. And so here's the setup. If they both got separate taxis, this is how we're going to determine the most fair way to split the bill. If Alice gets a taxi by herself, she'll pay $5 because she lives closer to where you live. Okay? If Bob went and got a taxi by himself, he'd pay $12, let's say, because his house is farther away. The fare for both of them together, because you just stop really quickly and Alice runs out, it's still $12 if they both share a taxi. See that? So, okay, how should they split the bill, and how does it be fair? Okay, so notice that if they split it in half, like it's a $12 bill, $6 and $6, that's absolutely not fair for Alice, right? Because she'd pay $5, she should have just gone by herself. That's not fair. Not fair. What is a fair value then? There's a couple different ways to define fair, but we're gonna do one way that's very similar to the Nash equilibrium prisoner's dilemma problem. So one fancy new term is called the Shapley value. Excuse me. I'm allergic to the outside right now. So one fancy term that we could use is called the Shapley value. It's a number that we can calculate. That's going to give us a good way to share this bill. All right. It has to do with taking averages again, just like the Nash equilibrium did. So yeah, the secret is the way to calculate this Shapley value and determine the best bill is you consider all the different ways, all the different permutations, the scramblings of who pays the bill first, right? Who pays the remaining bill in what order? That's a weird way to think about it. And then you take the average over that. So let me try and explain what I mean by that. So here's what you consider. So let's say Alice pays first, and then Bob pays. That's one ordering of the payments. Or Bob could pay first, and then Alice would pay. And the idea is they pay their fare, and then the next person pays the rest, whatever's left of the total. So there's $12 to spend, and if Alice goes first, she'll pay the full $5, right? She's paying her way through, and then Bob will pay the rest. So that's $7 left to make $12. Okay? Otherwise, if Bob goes first and he pays his bill, he's going to pay the full $12 to get to him, and then Alice, that's the full fare, Alice has to pay nothing if Bob goes first and he pays in that order. Who pays the remaining bill? That's kind of the setup. And then what you do is you take the average. You take the average, and you can focus in on anybody. Let's focus in on Alice. Just like we focused on prisoner A, for example. Let's take over these possible outcomes, these possible interleavings. Let's try and figure out what would be the cost for Alice on average, Alice's cost. Well, in this situation, she'd pay $5. And then in this situation, she'd pay $0. And the most fair way, according to this Shapley value, one definition of fairness, is, all right, take the average over those possibilities, and that's how much Alice should pay. Average, that is going to be $2.50. And that apparently is the fair price. So when you're sharing an Uber, now you know. I wonder if the app does this for you already, but Alice should pay $2.50 because normally she'd pay $5. That's still less. And then Bob will split the rest. He'll be like, is it $9.50, I guess? He's still saving money. And then Alice doesn't have to pay like $6 because that would be like splitting it. That's too much. Might as well go by yourself in that case. But over these possible outcomes, if you take the average, apparently $2.50 comes out. And that is how much Alice should pay. That's one way to calculate it. So you can play that game with your friends now, whenever you share an Uber or Lyft or something. Or a real taxi one day. I don't know if you go to New York or something. Any questions about that? So that's a fun little idea. It's a useful outcome. Now we know how to solve this problem. So that's definitely a cooperative game, or it's definitely a good idea to form those alliances and take one taxi rather than two. All right. For my last major example for this set of slides, let's talk about tic-tac-toe. I'm going to teach you an algorithm, a simple algorithm. It's called Minimax. It has a cute name, and it's a way to solve for the optimal strategy for any game that has tic-tac-toe-like properties. All right, so it's a kind of search algorithm. It's something you can code up, so it's useful. It shows you the optimal strategy to play some game. And so let's do it for tic-tac-toe because that's easy to think about. So let's imagine that this is what our current tic-tac-toe board looks like. I know it's an easy one to finish, but let's talk about the simple solution. We want to programmatically find an algorithm to always figure out the best possible move to play for the given player. Let's pretend it's X's turn right now. What do you do? How can you play this game? Essentially, the answer is, what Minimax does is it simulates the rest of all the ways that the game could be played. So X could make a mark, and then the board might look like this, or X could go here, the board will look like this. X could go right here, the board might look like this. You have all these options, right? I'm supposed to draw a game board, not next. All these different options. I guess there are 3 options, right, for where X could go here. And then it's O's turn, and then you kind of fill in, okay, if X made this move and the board looks like this, then O could make a move and now the board looks like this, or O could make another move and the board looks like this. I guess there's 2 slots left after that, right? So each of those would look like that, and you can just fill it in until the game has been won by somebody or the board is full. So that's why you can simulate the rest of the game, and the Minimax algorithm works like this. It has min and max in the name because you flip turns when you take turns as you play. So when it's our turn, we're trying to, if we're X, we want to make the move, these are our moves right now. We want to choose the move that maximizes our chance of winning. And then as we're simulating the rest of the game, we're going to simulate the entire game, on this next level, it's O's turn, our opponent. When it's their turn, we have to assume that they're experts at tic-tac-toe, and they're going to make the move that minimizes our chance of winning. So that's the trade-off. When it's our turn, we try to maximize our chances. When we have to simulate the other person's turn, we're going to assume that they're going to take the best move for them that minimizes our chance. So the goal is to calculate what's our best move in light of all the different options, in spite of all the different ways that O could try and win. Assume they're a really good player. They're going to make the best move for themselves. What's the best move for us with all that in mind? So that's the idea. So that's what Minimax is all about. And so, let's try this. Let's pretend you're the computer. Take out a piece of paper, open up Paint or something. Take a few minutes to try this. If this is your game state, if this is what your board looks like, make a chart of all the different ways that the game could be played all the way to the end of the game. See if you can figure it out. So I'll do one, for example. One way that this game could be played out looks like this. X could go, if it's X's turn, let's pretend it's X's turn. X could go right here. So then the board will look like this. X, O, 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 X1 here, X, X. Then you have some more options, maybe. Fill those in. And then also, now it's O's turn for this board. You got like 2 options, right, to go down, because you got 2 slots to fill. So see if you can fill in O's moves as well, if you can. Get it all the way down to the bottom, but start with this level at least. See if you can fill that in. And then we'll solve for the optimal outcome. I'll show you how to like give a score to all these boards. Okay? And then you can generalize this to like a more blank board where the game isn't already over. So give that a try. Because the goal is to assign a number to good moves, and like a high number to good moves and a low number to bad moves for us. I think I drew more lines than I needed to draw, didn't I? All right. I think you had the right idea. Let me do it for you. Starting from this state, what does the game look like? It was X, O, 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 X, X. And then, like, there's 3 places, if it's X's turn, there's 3 places that X could move to. Like here, here, here. And I will do my best to spread these out so I can draw all the options. And then, through the magic of technology, I can copy this a few times. 1, 2, 3. Alright, what are all the ways that X could have moved? X could have gone here, X could have gone here, or X could have gone here. Okay? And notice right here the game is over. There's no more moves after that. After the game is won, of course. So, okay, you can fill in more for here. It's O's turn for this one. So there's 2 moves to make there. Is it worth copying and pasting in? Probably. And this is what a computer would do, just faster, of course. Go and enumerate all the different ways to win this game and have it play out. So, okay, if O could move, I missed the line somehow. O could go either, let's see, here or here, yeah? And then here the game is won. And then one more time, if we go here, we fill it in X, O, O, X, O, O. X could go right there because it's X's turn for that. Like it always flips. It's X's turn here, O's turn in this level, X's turn again on this level. It's kind of interesting how that works. And then this one, probably similar to the leftmost one. There's 2 ways to keep going. So X, O, 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 X, X, X. If it's O's turn right now, that O could go either here or here. If they went here, they won the game. And here, otherwise, we could go and win it like this, if it's X's turn. Does that make sense, what I just did? So those are all the different ways to win the game, or have the game end. Looks like in this case, somebody always ends up winning. What are all the ways to win? So here's, like, X wins here, for sure, on both of those. This one O wins. This one X wins. This one X wins. This one O wins. Okay, so the secret is, what Minimax does is, again, we're trying to maximize our chances and pretend that when we simulate our opponent, they're trying to minimize our chances. So we're going to assign numbers to each of these states, starting from the winning state. So like, we want to win, we're X. So if we find a game state where we won, we'll give that a +1 score. We'll say +1. If the opponent wins, we'll give that a -1 score. So +1 here, and then +1 to this one, and then a -1 to this one. And then as you move up, like, all right, we gave a score to this one, but what about this one? What's this one's score? Well, it's always, if it's our turn, this is a game board where it's our turn to make a move, we're going to try and maximize our chances. And so we take the maximum of all the options, because that's our job. We're going to take the maximum, and so there's just one option, so it's 1. So the score for this game board is +1 because we're going to maximize our chances. It's our turn. And then for this one, for this game board, it's O's turn, and we get to assume they're trying to minimize our chances. So we're going to take the minimum score to assign for that one. We're going to assume that if we choose this route, the way that the game will be played out, the way that O wants to play, they're going to take the way that minimizes our chances. So we're going to assume that they're going to immediately win the game if we ever get here. That's essentially what's happening. We're taking the minimum over these options when it's O's turn. So it's a -1 score to this game board. We kind of want to avoid it. See that? And then same for this one. This is +1 for us. We're maximizing when it's our turn, so +1 for this one. And then you give like 0 to a tie if you ever get to a tie. And then this one again, it's O's turn. They're going to look at their options and they're going to try to minimize our score. So they're going to choose the -1. So we're going to assign -1 as a score to this game. Because O, if they're a good player, of course, they're going to immediately see that they can win. So now when we're back here in our original state, we're trying to decide which move should we make. We're X. We're going to try to pick the move that maximizes our chance of winning. So we're going to find the maximum score among all the options. And do you see how there's only one left? Only one natural way to play this game. Of course, it's this one. And so that, it actually generalizes to game boards that aren't as filled in, like X, O, maybe O, X or something. Like, you can play it out. You can draw the whole thing. You can assign the numbers. And if it's X's turn, you can decide, all right, what's the best one to go down by doing the same idea. So that's a fun little algorithm to tie it all back to computer science. That's called Minimax. And if you ever take my CSCI 26 class, I will force you to implement parts of this in code. So that's a fun little idea, I think. Questions about that? All right, so let's see. Let's switch gears to another set of slides. And that will be the last new topic today. I want to talk about recursion. And I think recursion is beautiful. I don't think we'll get to the actual beautiful part, but we'll get to the recursion part today. So, recursion is a fancy word. It's a weird name. It's when you have a problem and you solve it in terms of itself, which seems like you'll never get to the answer, right? If you're just continuously giving the problem, what's 2 + 2? Oh, it's 2 + 2. It's 2 + 2. Like, you're using the problem inside of itself somehow. Like, isn't that circular reasoning? Like, aren't you just going to keep on wrapping back around and asking the same questions? I say no, because I have an idea. Oh, now it works. Weird. The secret is we're going to treat the problem like it's one of these like Russian stacking dolls. Recursion is all about finding a problem inside of itself, but like you have your original problem that somebody's asking you. The way you could eventually solve it by finding that problem again is that you find a smaller version of the problem. And then that version of the problem finds a smaller version of itself and finds a smaller version of itself. And it keeps going until that you get to a problem that's so small, it's immediately solvable, and then you start stacking it up. And you eventually find the answer that way. That's what recursion is. You find yourself inside of yourself in a smaller way. And so this is a hard problem in computer science, hard topic. So there's a lot of memes about it. And then it can also be used to like play little games. If you've seen this kind of game before, it's called the Tower of Hanoi. It'll tell you, like, there's only one way to solve this game, and it's a recursive solution, surprisingly. So it's worth learning. It'll tell you how to play this game and move all the pegs with the right rules over to the other side. So, yeah, it's not circular reasoning. As long as the problem gets smaller, everything will work out. This is what recursion is. It's when you solve a problem in terms of smaller versions of that problem. Like, here's your original problem. What you do is you go and you find the smaller box within the box. You find a smaller version of that problem. You solve it. And then somehow that answer, you can use it to build up your own answer. That's the secret. And then this one will be defined in terms of itself. It'll loop all the way down there. It's kind of another way of looping, which is kind of cool. So yeah, here's the setup. You find a problem that has that problem inside of itself somehow. We call that smaller problem, the one you see inside of it, the sub-problem. And then we notice, the way that recursion works is you'll notice that you can use that sub-problem's answer. You can add it, just do a little bit of extra work to solve that original largest problem. So that's the answer. That's the secret. So here's my question to you. I'm going to give you an example of factorial. So I claim that finding the factorial of a number is a recursive problem. So like if you ask for 5 factorial, there is a smaller factorial inside of 5 factorial. So like write out 5 factorial. What's that equal to? 5 times 4 times 3 times 2 times 1. Do you see the smaller factorial within 5 factorial? Discuss with your neighbors for a second. Do you see it? Is there a smaller factorial there? Maybe there's many.
Yeah, it's 5 times 4 times 3 times 2 times 1. You do like 5 times 4 factorial. Yep, 5 times 4 factorial. So basically, how you would write this out in a function would be like, call the function within the function. That makes sense. So if you like have factorial 5, then in the code of that function, it would be the number that was given times the factorial of the number that was given minus 1. And then that would go until it reaches 1. And so if it's like, if the number was 1, then just return 1. Because 1 times 1 is 1.
There's 6 factorial, that's for sure. But does everybody see how factorials are just like a number and then all the way to 1 multiplied together? There's also more than that. Yeah? There's a bunch of factorials. There's a bunch of smaller ones. Here's 4 factorial sitting right there, secretly. Here's 3 factorial, right? And then there's 2 factorial right there. And then technically this is 1 factorial right there. See how all these smaller factorials are there? That's what it means to be a recursive problem. You can find it inside of itself forever. Until you get down to something so small, you have the answer already. So that's the secret. Does that make enough sense right now? Just circling that. Because that's going to do it for us. That's going to show us a different way to calculate the factorial of a number rather than looping. It'll be interesting. Code for this. So yeah, finding the factorial of a number is the recursive problem. We noticed that 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Sure, but we found a smaller factorial. We found 4 factorial. Usually when it's recursive, when you have a recursive problem you're trying to solve, you want to find the next smallest one. It is cool that they're all there, but you want to find just 4 factorial. You're looking for the next smallest one. So, you found it. So another way to write 5 factorial then is 5 factorial is equal to 5 times 4 factorial. See how that's the same? That is the right answer. That's kind of interesting. That's us using 4 factorial to build up that final answer. If we wanted 5 factorial and somebody gave you 4 factorial, do you see how you could just multiply by 5 and have the answer there? That is the powerful secret there. And that's really nice. This is a smaller problem, right? A smaller factorial finding problem. Cool. And it generalizes. Everybody looks like that. Like 7 factorial, what's that? 7 times 6 times 5 times 4 times 3 times 2 times 1. But really, it's 7 times 6 factorial. 5 factorial is equal to 5 times 4 factorial. 7 factorial is equal to 7 times 6 factorial. Do you see that generalization? That works for most numbers. How do you calculate n factorial in general? Just follow this pattern, right? N factorial is equal to n times n minus 1 factorial. See that secret there? N factorial, you asked for that, that's equal to n times n minus 1 factorial. Most times. See that? That's us defining the factorial problem in terms of smaller versions of itself. And this is called the recursive case of the solution. So I'll write that in green. Recursive case. Alright? And you can use that, and this works most times. But eventually, you want to have another rule in addition to this one, in addition to the recursive case. We need a way to stop. It's called the base case. So let's run our rule. Let's try it out. Let's watch it work and see if it ever breaks down. Once it breaks down, we know that we want to stop by that. So we'll say, all right, 5 factorial. I want to know the answer to 5 factorial. What is it according to my rule? Just plug in 5 for n there. 5 factorial, well, it's equal to 5 times 4 factorial. And that makes sense. And now I have a smaller factorial. I can run this rule again. All right, well, how do I solve for 4 factorial? Well, that's equal to 4 times 3 factorial. Just plug in 4 for n. See that? And that's still that's still logical. That makes sense to ask for that. That's correct. All right, let's keep running it. 3 factorial using our recursive rule. That's equal to 3 times 2 factorial. Yeah? And that still makes sense. 2 factorial is equal to 2 times 1 factorial. 1 factorial, all right, what's that? According to our definition, it's equal to 1 times 0 factorial. And this is kind of where it stops making sense, right? 0 factorial technically is defined in math to be 1, so you could go further. You could go one further. You could be like, all right, what's 0 factorial according to my definition? That's equal to 0 times negative 1 factorial, right? And so this is where it's definitely not making sense, because the second you add that answer in, first of all, there is no such thing. There is no answer to negative 1 factorial. It does not exist for negative numbers. And then also, once you multiply by 0, like the whole answer is 0. And we know that 5 factorial is not 0. So like we went too far here. We should have stopped before then. And so you could have stopped here, like 0 factorial, you can just define it to be 1. But honestly, it probably makes more sense in your mind just to be like, all right, if you ever ask me for 1 factorial, like that's the one I know I'm done with, right? If you ask me for 1 factorial, I'll just tell you the answer is 1 and call it a day. See how that stops it all? It cuts us off so that we don't go further and get into weird territory there. That's called the base case. Like that's when we immediately know the answer to n factorial, when n is 1, without having to compute n minus 1 factorial using this recursive rule. Base case. That stops us. That's kind of cute. So let's code this up. There's a way to code this up, and it's a recursive way. And usually when you solve problems in code, you write it like a function that does it. You're going to make a factorial function that solves for 5 factorial or 7 factorial, factorial of n. So we're going to write then a function called factorial that asks for the factorial, and it's going to be a recursive function, right? So this is going to be very interesting, right? So we're going to make a factorial function. So we'll say like def to define the function. Def, call it fact for short, fact of some n, and this will compute factorial of n. So compute n factorial. Bless you. And so if you say, well, I'm getting ahead of myself. So now we're supposed to give back the factorial of whatever n was. And essentially, we just implement it using these rules. It's like, use the base case rule if you're in the base case. Otherwise, use the recursive case rule. See how that'll be an if statement? Like, all right, what was n? Was it 1? Did somebody just ask me for 1 factorial? Because if they did, I have the answer immediately. If n is equal to 1, that's the base case. I know that answer right now. Base case. Just return 1. You ask me for 1 factorial, the answer is 1. Else, now, if it wasn't that rule, it wasn't this one, it must have been this one. It must have been the recursive case. And how do we program that? This is where it gets really weird. Recursive case. Because we've determined, right, that n factorial of some arbitrary n that's not 1 is equal to n times n minus 1 factorial. So we need to figure out n minus 1 factorial right now. We need to get that answer so that we can multiply it by our n, and that's our final answer. We see that? So this is like a chicken and egg problem now, because it's our job to be calculating the factorial, and I need it for a smaller number. I need it for n minus 1. I need to multiply n minus 1 factorial by n, and that's my final full answer. And so because it's a smaller problem, you can call yourself a recursive function asking for the factorial. Well, it's our job to calculate factorial. A recursive function must call itself because the problem is defined in terms of itself. All right, I need the answer to factorial of n minus 1 before I can do anything. I'm the one computing that. I'll send it to myself, a smaller version of myself. This is where it gets a little weird and magical. It's like, that is so interesting. And then once I have that, I called it x. Once I have that answer, just multiply my n by that, and like that's the whole answer to the original factorial of n. So return n times x. See that? And so this is a smaller call. It's called the recursive call. It's us programming our recursive case. You have to call yourself because it's your job to calculate the factorial. You hand it off to yourself. And so, for example, if you call fact of 5, do you see how you're going to hit this case? Because 5 is not 1. And you're going to go off and you're going to try to first calculate the factorial of 4, which is kind of what you need to do, right? You need that answer so that you can build up the final bigger answer. And this just seems like it'll get you nowhere. It's circular. But because you're making smaller and smaller calls, like fact of 4 will call fact of 3 for the same reason, you'll eventually get down to the base case. You will eventually get to a stopping condition. And then you'll start building your answer right back up. All right? So let's code this. Let's code this up and see and watch it work. Because really, like normally, if you were doing the factorial of a number, I think I might have shown you that before, in code, you would be essentially doing, where is this code? You'd be doing a loop, like a for loop or a while loop. But no, we're essentially looping with function calls. By calling ourselves, it's so odd. So yeah, let me open up idle for this. And let's program this. It's so weird. What, let's see. What lecture are we? We're lecture 29. So I'll make a new file. I'll save it in a lecture 29 folder. Or no, it's on my desktop, isn't it? Where the world is my desktop? There it is. Okay. This one, lecture 29. Right? Yeah. And I'll call this fact.py for factorial. Okay. So here it is. Here's the code that we determined we need to write. So this is a function that computes def fact of n, lowercase n, and a colon there. And this is meant to return compute n factorial. All right. Well, we're either in the base case or the recursive case. If we're in the base case, n is 1. Somebody asked us for the factorial of 1. We return 1 because the factorial of 1 is 1. Otherwise, or in the recursive case, where we determine that we need to return Rn. The answer is Rn times n minus 1 factorial, and it's our job to calculate factorials, so we have to hand it off to a smaller version of ourselves. Fact of n minus 1 right there. And return, once we have that answer back, return Rn times that value. And that will build up the full factorial. Because like if you ask for 4 factorial, right? Once you get 4 factorial, if you want 5 factorial, just multiply it by a 5 out in front, like we determined. So that's pretty interesting. And so here, let's watch it work. We'll say print fact of 5. And 5 factorial, 5 times 4 times 3 times 2 times 1, that really is, you can ask the REPL to confirm, that really is 120. And so it looped, it got to the answer eventually, just by doing this, by calling itself. Isn't that crazy? And we can print how it's calling itself, because it's smaller calls, like fact of 5 was calling fact of 4, and fact of 4 was calling fact of 3, all the way to the base case. We can say print inside fact of n. Something like that. Maybe we'll have to make n a stir for a second. Watch. See how we're inside fact of 5, who's waiting on fact of 4, who's waiting on fact of 3, 2, eventually we're in the base case. And then, alright, we hit the base case and it starts returning back. Then 2 has what it needs, then 3 has what it needs, then 4 has what it needs, and 5 finally has what it needs for fact of 4, and it can give back its answer there. Isn't that interesting? That's so cool, and it's going to work for any number. Same with, like, fact of 3. That will correctly compute 6. 3 times 2 times 1. For the same reason. Fact of 3 we'll call fact of 2, which we'll call fact of 1. It's like looping using functions. It's so weird. But some problems can only be solved recursively like this. So it's worth learning about. It's such a cool way of thinking. And so let me draw for you why factorial is giving back the right answer for factorial 5, for example. Why is it giving 120 back? Why is that working? Why is this code that doesn't have any loops in it really loop? So that'll be fun. So I'm going to use what's called a stack diagram. I told you a little bit about that before. It will talks about how functions are calling and who they want to return back to. So let me draw that again. So remember, like I drew this diagram, like we were in the outermost code, for example. And what was our outermost code? Let's say we're here. We're trying to print the fact of 5. So that's what we really would like to do right now. Print fact of 5. That's the first piece of work to do. So I'll put it on my stack of work to be done. Fact of 5. Print the fact of 5, please. So this is a stack diagram. Remember, it's a stack of work to be done. And also, it tells you who wants whose answer. A stack, the person below you wants your answer. Stack of work to be done. It models function calls and who they return to. Work to be done / who wants whose answer. Okay? So, all right. Print sees, all right, I need to print whatever fact of 5 is. It doesn't know the answer, so it has to go off and it has to compute fact of 5. So before we can print anything, we have to call fact of 5 to actually get a number back, and then print is happy to print that. But it doesn't know what the number is yet, so it has to go off and ask the function, hey, go compute fact of 5, please. So print is waiting on fact of 5. So there's 2 things that are currently running at once, right? Print is just sitting there. It's like, I need fact of 5's answer, so it jumps up here with n being 5. All right, so we're in this code. N is not 1, it's 5. And so we have to calculate this x variable. We have to fill it. We make a little x variable for ourselves, a local variable. We got to fill it with the answer to fact of 4. We don't know what that is. So we have to go off and call ourselves fact of 5. You see how it's going to sit on this line and wait for fact of 4. So fact of 5 is not done. It does not have its answer. It needs fact of 4 before it can continue. So it's sitting, waiting on this line, fact of 5, and it's calling fact of 4. So now we're back. 2 versions of fact are running at once right now, which is crazy. Fact of 5 is sitting right here, but fact of 4 starts with n being 4 now. And like it's all right, it's not in the base case, so it's going to again try to make an x variable, its own separate x variable, which it needs to fill with fact of 3, right? Because n minus 1 now is 3. Fact of 4 needs fact of 3 before it can give an answer back. It needs to go off and compute that. So fact of 4 goes and asks fact of 3, hey, go give me that answer, please. I need it before I can continue. So factor 4 is calling factor 3. And now there's 3 versions of factorial that are all happening at once. They're all waiting on each other. Print was waiting on factor 5, who's waiting on factor 4, and now factor 4 is waiting on factor 3. They're all on this line, right, trying to get the smaller answer. We haven't gotten it yet. So now factor 3 starts. Factor 4 calls factor 3, and so we jump up here with n being 3, and we run the whole thing again. Another version of the function. It's not 1. 3 is not 1. So factor 3 requires factor 2 to be computed, because then it will multiply its 3 by that and then give that answer back. So factor 3 needs to go off, again, make an x variable, a local to it. I need to know the answer for factor 2. Tell me, because I can't give you back factor 3 without that. I need that first. So it's going to sit waiting on this line again. See that? So factor 3 calls fact of 2. We're getting there, getting down to the base case. Factor 2 now. So there's 4 versions of the function that are all running at once. Just the person on top is who's in charge. Everybody below is waiting on the person above it. So factor 2 is here. Like, all right, we jump here. 2 is not 1. And so factor 2, again, is going to try to make an x variable to hold factor 1 because it needs the answer for 1 factorial before it knows the final answer for 2 factorial. That's what the recursive rule requires. Factor 2, trying to make an x variable. Like, I need factor 1, please. Give that to me, then I can give you back factor 2. So factor 2 calls factor 1. Are you guys following me still? There's a lot going on. Factor 2 is calling factor 1, and that is going to kick us all off, and it's going to finish it. So factor 1 is the base case. Now, again, notice there's 5 versions of factorial that are all running at once right now. Everybody below is waiting on the person above. And we just really wanted factor 5, but it needed all these previous answers to get there. So factor 1, who factor 2 is waiting on, is running right now. So there's a person on top of the stack, so they're in charge. They're doing all their stuff. And finally, yes, n is 1. So factor 1 returns the number 1 back to whoever called it. And it's always the person below you on the stack that you're returning back to. So factor 1 is returning the answer of 1 back to factor 2, and now its work is done. I should be erasing it, but I'll just draw a slash to mean that factor 1 is finished, and now it's factor 2 who's the star of the show. Factor 2 is in charge again. So factor 2 just got an answer back for factor 1. See that? And it's storing it in its x variable. Got 1 back. It saw the 1. It's going to place that in its x variable. That's its 1. I was like, all right, I know how now to calculate the factorial of 2. I'll multiply my 2 by 1 factorial, which I know the answer to now. I know 1 factorial. I've placed it in my x variable. I'll return my n, which is 2, this is factor 2, times that answer for the factorial of 1, times 1, and that's my answer for factorial of 2. And so it's going to multiply 2 times 1, and that's its answer that it gives back to whoever was calling it. And then it's done with its job. It's returned. Do you see how that was the correct answer for the factorial of 2? And it just gave it back to whoever was waiting on it, which was factor 3. So now we're back here. Factor 3, everybody was waiting on this line, right? Factor 3 was waiting on this line for factor 2, because once it has 2 factorial, it can multiply its 3 and give it back. So it now has an answer back for factor 2. It just got it back. Return to it that answer for 2. Factorial of 2 is 2. It's placing that in x, in its local x variable. And it's like, all right, I'm ready now. I can multiply my 3 by 2 factorial, which I know the answer of now, to make 6. And that's what I return to whoever was waiting on me. So it's returning 6. And do you see how that was the correct answer for the factorial of 3? It really is going to build itself up properly, eventually, slowly but surely. And then who was waiting on for the factorial of 3? It was the factorial of 4. Factorial of 4 was sitting right here on this line waiting for the factorial of 3. It just got the answer back 6. It sees that 6 now. There it is. It has it. And it knows, all right, I know how to calculate factorial of 4 based on the answer to factorial of 3. I'll multiply my 4 by it. And that's my answer for the factorial of 4. Factorial of 3, which was, I got the 6 back, placed it there, times my 4, that's 24. I'll return that to whoever was waiting on me. And so now we're back in the original call, finally, to factor 5, who's waiting ever so patiently on factor 4, who now got an answer. Factor 4 says, oh yeah, my answer is 24, and it's going to shove that into x. Factor 5 was waiting on that. Now it has an x variable populated with 24, and factorial of 5 is like, okay, I'm ready. I'm ready to do my job. To calculate the factorial of 5, I know that the answer is always my 5 times 4 factorial. I just got the 4 factorial answer back sent to me. I waited so patiently. That's an x right now. I'll multiply my 5 by that value, and that is my factorial of 5. And so it's going to compute 24 times 5, which is in fact 120, and that's what it returns back to whoever was waiting on it. And it was the print call that was waiting on the factorial of 5. It just needed to know what this answer was so it can print that real number. And so now print sees 120, and it's like, all right, here's the output screen. It's like, okay, 120, I can print that for you. And now print is done. We're back in the rest of our code. And that is why factorial works. Eventually, like everybody's going to start asking the person below it. 5's going to ask 4, 4's going to ask 3, all the way down. Eventually, we're going to make our way to the base case, and then it starts unwinding, we say. The stack unwinds, and then they all start returning to whoever was waiting on it. And eventually, like each smaller problem, each smaller answer is building up the next bigger answer, is building up the next bigger answer, is building up the next bigger answer, until we have the original problem solved and returned, and we return that final answer to whoever really needed it, which was like the print call. Okay? So that is the exciting story of recursion. And so I know with factorial you can just as easily have made a loop like for I in range all the way up to 5, right? You could multiply values together. You could do that pretty easily. It's just like summing values as well. We did loops for that already. But it's worth learning recursion because some problems, like this one, maybe you've seen it before, called the Tower of Hanoi, where you can only place smaller pegs on top of larger pegs. This thing, like, you'd be hard-pressed to like list out the steps to solve it, to play the game to completion without using recursion. Okay? And so that's one thing it's good for. There's a lot of more advanced computer sciencey things that it's good for, but it's just so powerful. It's looping without loops. And so I think it's very, it's a beautiful little concept that will show up a lot if you become a computer scientist. So yeah, I think that's what I wanted to say about that. And that's where I wanted to stop on recursion. Any questions about that? Cool stuff, I think. Yeah, so those were the two things I promised to say today, and I think it would be evil to give you any more assignments, because we have just one more week of classes and then the final exam. So I think that's all that I wanted to say today. The rest of the time is yours to ask me questions and stuff.